Should I show my screen, right?
Yes, yes, absolutely.
Yeah, so I took some pictures of rovers in Innopolis, like on nights, on day, like far
Nice.
away, close and stuff.
Nice.
So, okay.
Now go to RoboFlow's website.
Mhm. Okay.
Create an account on the right.
Mhm.
Yes. Mhm.
Mhm.
Projects, yep. Okay. Yes. Wow. No, yeah. Okay, create new project. Yep. Nice. Same. Okay, very nice.
Okay. All right. Yeah, and then I just do this.
Yes.
I have to convert them. I took them on my iPhone. Okay. Crap.
Oh, wow.
Oh no.
This is gonna take some time, huh?
Well, I think I can do it in one click, but I'm not sure yet.
See.
I can export them as PNG.
Wow.
Yeah, I'll have to. Yeah, okay. So I upload one picture. Okay. Yeah, I'll just do one and then I'll do the others later. Okay. Okay, so what now?
Now you will start to annotate. Can you go to annotate? Oh, you already annotate. Okay, just assign it to yourself. Yes. Okay. And now you will have to choose. Nope. You see on the right. Okay, this is okay too. You see on the absolute right. Yes,
This
you
one's
have the option of polygon tool. Use a polygon. It's much better.
okay, so
delete that one. Yep, and restart.
so I need
There
to
you go. Yes.
wait, what?
Is it on?
Should I drag it or?
No, just clicking. Just clicking. Click a lot more.
I see. Okay.
Okay. Uh-huh.
Yeah, but why are we doing it in polygons if we will be recognizing boxes?
Yes, because for now we are working with object detection, but for next week's lecture we're gonna be working with segmentation. For segmentation,
okay.
you need polygons. So it's best to prepare, over prepared rather than under prepared.
Okay, I see.
Okay, perfect. And that's
okay,
it.
and
A great example. This is a great tutorial for what we're going to do today. Thank you so
Mhm.
much.
Okay.
Now,
Yeah, thank you.
I think Paulina has already done this part. Do you want to share your screen too?
Like I can, yeah.
Go ahead. So we're gonna do the lab from Paulina's laptop, okay? Amazing. Now can you go to generate? So you have already annotated all of these pictures.
Yeah, that's a mirror data set. I just
great work.
walked around in Innopolis, yeah.
Can you go to generate?
Generate, yeah.
Generate a new version and you are already there. Train test split is amazing. Pre-processing. No, all good. This is great.
Continue.
Yes. Augmentations. Now try to add some augmentation steps. Nothing, not too much. Okay, let's start. Maybe some cutout and mosaic. Yeah, apply.
Apply. Okay.
That's it. That's enough. That's enough for today. It will be too long for you. Yeah.
Okay.
And then continue. And there you go. Generate. And we're generating. Let's see. Perfection. Export data set. It's on the top right. Yep. Amazing. Select the format.
I
No,
think
click select the format. Don't.
ah,
Yes. So for this one, let's start with YOLO V8.
yellow
see?
V8.
So from this place, the click the show code is much better.
Okay.
Yes. So from this location, you can choose anything you want. You could choose YOLO V8. You could choose any type of model you want to train, and it will automatically convert your data set to the format that is accepted by that model. So this is like honestly the hardest part of our job as, people who are going to train object detection models. And this is already being done by RoboFlow, completely automated. So you're not going to worry about any of this. Now press continue and let's see how easy it is. Amazing. Starting to download. Perfect. You're gonna have some code.
What?
It's gonna come up soon, I think. I hope. Here it is. Just copy this code. You see that double rectangle? Yep.
Yeah.
Now what you're gonna have to do is, you see, paste this snippet into a notebook from our model library. Click on the first link. Yes. Open it in a new tab. Go to it. Now choose YOLO V8. And on the right, you can see the word Colab Notebook.
Oh.
No, it's okay. Yeah, Colab Notebook. Perfection. Yep. So if you'd like to know a little bit more about YOLO V8 and what's different between this version and the version we studied in the lab, easy. They have a beautiful video of them training it, and they have also a paper that describes basically the differences. We will see the differences for YOLO V4 and so for some of these models, but not now. For now, we're just going to continue the lab with Paulina. And as you can see, it's very simple, just a couple of clicks, right? Now copy to drive. It's on the left, yes. Copy to drive.
See.
Perfect. Change the name soon. Yeah, after it does its work. Change it to something that you want to do, like, I don't know, mirror detection using YOLO V8. YOLO V8 mirror detection. Perfect. Nice. That's all you're going to have to do. Now start running the code. Like, go down a little bit to the code. Yeah. Start running it. Yep. Perfect. Perfect. See, so far, so easy, right?
Pretty easy, yeah.
Yes. Yep. No worries. No worries at all. Continue. Yes. Here, you see that place where you have to put your data set. Go up a little bit. Up, I think. Up a little bit. Here.
Oh, yeah.
Here you will have to paste that code. Just the final four. No, just the final 4 lines. Yes.
Oh.
Yeah. It's okay. Nobody's gonna steal it. No worry.
Yep.
Steal your friend's API key, huh? And now you will just have to rerun from that point and go down, and there you go. You have already a pre-trained or a fully trained YOLO V8 model.
Interesting.
See, super easy. Okay, thank you so much, Paulina. Then let's wait to see if it actually does the training or not. Let's see if it was super easy or not. Yeah. Okay. So you see, it failed mainly because you still did not go up a little bit. Rerun. Yes. Now it should work. Is it downloading? Yes, it is downloading. It is installing. Now it is downloading.
Oh, yeah, it's downloading.
Let's see. And it is downloading it in the format that you need to immediately start training. So you don't have to do any conversions between the different versions. As you have seen, that list contains like a lot of different versions of the data sets. Some of them they use text files, some of them use JSON files, some of them use YAML files, XML files. Some of them they use like the representation of the box as 2 points. Some of them they use it as the central point and the width and height. Others they use it as the central as the top left point and width and height. So it's really there are so many different how do we say so many different versions of how you can read these kinds of data sets. And now it is training, as you can see, 1 epoch out of 25. Immediately everything has been done for you guys, and it is already doing very good transfer learning using the techniques. Remember when we studied fine-tuning techniques where it replaces some of the layers, especially the classification layers, because there is a difference in the number of classes. All of that being handled for you behind the scenes. And as you can see already, your MAPE 50 is 0.93, which is already very, very good, right? So it's already perfection. After 2 small epochs, your model is already amazing. Okay, thank you so much, Polina. Now it's my turn to show you guys some of the other code for a bit more complicated models. So this was for YOLO V8. YOLO V8 and YOLO V5, super easy. They're like the easiest thing. As you have seen, it takes less than 5 minutes to get fully started with training them and even having their results. Now we'll do one which is a little bit harder, which is YOLO V8, YOLO V4. So let's do it. We go to versions or to generate if you don't have a version already. Export YOLO V for this one, YOLO Darknet. This one is the hardest model that you could ever train because it requires a lot of manual configurations. So let's see how this one is done. If you already this one, you should be pretty good to go.
Cannot see your screen.
Oh, sorry. Yeah. All right. So let me do it from the start. Select YOLO Darknet. As we said, this is the hardest one. All the others are pretty easy to work with. TensorFlow, object detection, all of these are pretty straightforward. The only one which is extremely difficult to work with is this YOLO Darknet model, mainly because it's written in C and not in Python, right? So it's a little bit out of our comfort zone. Copy it, and we're done. So here we come, and let's look for YOLO V4. Darknet. Colab notebook. Okay, here it comes. Copy to RoboFlow, copy to Drive. All good, let me give it a name. YOLO V4 Darknet P-Lab. Amazing. So as usual, what we're gonna do is just run the first code. This code is just here to install the appropriate config for our specific, what is it called? Our specific GPU. So right now we're compiling basically the Darknet framework. Darknet is just basically TensorFlow or PyTorch, but for C. So it's the equivalent of the framework that is used to train your basic, what is it called? Neural networks, but in C. We're not going to go too much in detail, but what's really happening here is that it's looking at the characteristics of your GPU, and it's already, embedded with the characteristics of the most common GPUs that you would find on Google's Colab. So for example, the V100, its Gen code architecture is Compute 70, and this code is SM70 and Compute 70. So this one is SM75, Compute 75. This one is SM37, SM61, It depends. Whatever GPU you're using, you can find these characteristics with a simple Google search. Put them in, and simply all you have to do is replace them in the start in here. This is the make file. Yes, here. Just change this file, just change this line with whatever config you have found for your specific GPUs, and immediately just run it. And it is now compiling. Okay, it finished the compilation. And now you should have a file. Let's see, darknet. There should be a darknet file in here that you can just run. Can you see it? I cannot see it. Let's see if it was correctly installed or not. Okay. Let's get this. So we're downloading the dataset right now. There we go. So we will speak about these config files. I just want to confirm that it actually runs correctly. And the darknet was actually yeah, this file. Yes, no such file in the directory. Let me check why. So it was not installed correctly, right? Yeah, I don't see it. It was not installed correctly. Go back here and let's make it. Let's see. The issue is the GPU that Colab gives you is somewhat always random. So sometimes you might face some issues with installing C libraries immediately, but let's check. Which one did they give us? Tesla T4. Tesla T4 should be a pretty common one. Yeah, we have it. So technically it should go fast. Let's see. Yeah, correct. There was an error. Let's see. Yeah, there was a error in the compilation. What was the error exactly? If I'm not mistaken, it's a error in their code, just a bug. That is a unclosed array, but I have to find where it is. Undeclared first use in this function. Did you mean? Yeah, it's okay. I guess we're gonna have to look for another model instead of YOLO v4. It's always the hardest one to actually get working. But at least you know how it's a thing. Let's go for YOLO v7 then, since we've already seen YOLO v8. Okay, we're good. Let's look at YOLO v7 for instance segmentation. Amazing. Check its Colab notebook. This one should be relatively easier, if I'm not mistaken. Yeah, well, it doesn't seem like it's using C++, so that's good. Run anyway. Yeah. Install. Okay, so it's a Python code, so that's great already. Pip install, amazing. This is great. Wonderful. Okay. Now let's check where can we train it. Yes. right? So here it's actually performing the segmentation. So this is just segmentation on a random image. Here's the person, here's the dog, and here is a car. Pretty well, right? Very good results. Now let's actually train it and see how it works on our data set. So here is downloaded the data. Amazing. Let's see. Now we're gonna just be training it for segmentation. Epoch or batch size is 16. Epochs are for 10 epochs. Device is good, everything is good, everything's good. Now let's see. So here are the layers. Oh, we got a message here. For training our model, since it's the latest version, or so yes, the actual latest version of YOLO is YOLO v3. All right, so there was YOLO v1, and then there was YOLO v2, and then YOLO v3. This is the actual order that was done by the first authors of YOLO, right? They are the creators of YOLO. After they did the YOLO v3, they kind of stopped ever working on YOLO. And now you have YOLO v4 and YOLO v5 and YOLO v6 and YOLO PP and YOLO R and YOLO X and YOLO 7 and YOLO 8. All of these new versions of YOLOs are just different techniques to train the same architecture with different algorithms or with different pre-processing techniques. Just for example, as you have seen those augmentations, some of them they just change that. Some of them they change the loss functions. So the actual differences are very minimal. And there is no such thing as this one is new, so it is better than the previous versions, right? As it's not from the same author. So there's no such thing as the order of YOLO v8 is better than YOLO v7. But you are actually true. In this case, for me personally, I prefer either using YOLO v8 or YOLO v4. They still have the best results so far, much better than YOLO v5 or YOLO v6. But it's up to you. So some data sets, they work very well. For the Chinese version, which is YOLO PP, I actually really like that one. It does give very, very good results. And it has, I think, even better performances than YOLO v8. So you could try it. If it works for your data set, then that's great. That's great. If it doesn't, explore with something else, right? So it's pretty easy to do that. So here, let me just confirm what is it called? Everything is good. Yep. So here, for example, you see how it works for them. X1, X2, Y1, X2, Y2, X3, Y3. This is for segmentation, and this is how they represent the data. Thank you. So this is their way of representing segmentation data. First, you start with the, what is it called? The class index, and then you put the segmentation points, those polygons points that you were making by hand. How do you store this? You store it in a TXT file for each image. Each image is associated with a TXT file. And then, of course, you have this. And in this, we will have to basically fix it or maybe change it a little bit. Let's take a look at it. Where did we download the data? So where did we download the data? Let me check. Content segmentation here. Okay, here it is. Data.yaml. There we go. So we got 3 classes. I don't know what this is. I don't know what this is. I don't know what that is either. So this is a data set for, I think, the types of red blood cells. I don't think any one of us is expert enough to learn from it, but let's take a look. There's something wrong here also. There's a bug as usual. Boolean index did not match indexed array along dimension 0. Dimension 0 is 0, but corresponding dimension is 656. I do not get where this is. So it's starting to train. Let's see what happened. Plotting image sizes. So it is accessing the data correctly. It is loading it correctly, starting the training correctly, but then it reaches a bug. New segments, array, new segments at I. Let me check. Images are good. Labels are great. Yep, so probably this is just a bug in their code. Yeah. So sadly, their code is not maintained very, very well for YOLO v7 apparently. Let's check YOLO v8 then. It's a great website, but you're gonna have some bugs to fix. Let's check YOLO v8. Okay, YOLO v8. I think this is the latest model they have, so they should maintain it a little bit. Let's see. Okay, let me just close the other sessions, cancel. YOLO v4, terminate this one, and YOLO v7 also, let's terminate it. Perfect. Okay. Okay, so this one seems to work. At least YOLO v8 is well maintained. But the other codes also probably there's just like a small bug, so it's not really that horrible. Usually their code works very well, but I think there's always a difficulty with maintaining like 100 different models in your code. So here, as you can see, you can just use their model to train for, detections or making predictions for object detection like this, or for segmentation, or for even image classification. So their model is pretty versatile, and they have multiple versions of their model. If I'm not mistaken, it's already in this. So yeah, so here you can do classification or segmentation or detection. Sorry. And here you could do training, prediction, validation, or you can export the results. There are different types of or different versions of their model. There is the YOLO v8 Nano YAML, YOLO v8 Nano for classification, YOLO v8 Nano for segmentation, and there is this. This is basically the actual either the YAML file, and they will just download it, or you could just give them the actual weights for train or the pre-trained weights, right? And here they have also format ONNX, which is a pretty common format that you could use to actually deploying your object detection model in real life on NVIDIA servers or on immediately AWS servers. It's pretty nice because it's kind of how do you say, agnostic to whatever version your model was trained on. So whether it was trained on PyTorch, Python, or TensorFlow, or even C++ or C, this ONNX format is pretty good. So it can take, or it can be converted into it from any other type of model, and you can just run all of them as if they are all the same model. And here we're basically doing, as we said, model.predict. We give it an image. This is the confidence threshold for predicting, or what we will be taking. And this is something they should always keep in mind. If you are using a large model, then you should use a higher confidence threshold, because larger models are very confident about their predictions. So for a larger model, let's see an example of the dog again. Yeah, this dog, this is a small model, and I predicted this dog with like 0.29 confidence score. If you were using, let's say, the YOLO, a larger version of YOLO V8, let me check how many versions do they have? YOLO V8 already in here. Amazing. Let's see. YOLO V8, they don't compare it here. Let's see. They should have a comparison. Yes. So there's YOLO V8 Nano, which is the smallest model. It is definitely the lowest MAP. So this is the mean average precision. We will speak about what it is soon. But it has the highest speed in terms of what is it called? Inference speed for the model on CPU for ONNX, right? So here you can see it's 80 compared to this one, 400. These ones, as we said, they tend to have very low confidence scores, even for objects on which they are correct. Whereas YOLO V8X would have a very high confidence score, and we could check that actually right away and see how it predicts. Let's go down and see. So here for training for our lab, we're going to be training the Nano version because it's the fastest to train, as you can see. Already gives some very good accuracy numbers, the mean average precision numbers. This is already amazing. And as you can see, with a very minimal coding abilities, we're gonna let it continue working, and then we will see how can we use it, or how can we evaluate it. Once that is done, we will start speaking about what mean average precision actually is and how does it get calculated. It is extremely related to the concept of precision and recall, as you can guess, plus the concept of intersection over union. So it's kind of a combo between what you used to know in like image classification with accuracy, F1 score, and recall and precision, and what we have seen in the lecture, which is intersection over union. So you combine both of these into mean average precision number, which is extremely common in evaluating both object detection models and segmentation models. So let's just wait a little bit for it. And you know what? Let's not wait too much. Epochs is equal to 5. I think 5 is already too much. That's it. Just so that we have something that is trained weights. Let's see, runs here. Detect, train 1. There we go. We already have some weights in here. This is the arguments, if you want to remember them. You're training using SGD. You could try to train maybe with Adam or something else. Here you will find things like those pre-processing that we spoke about: scaling, shear, perspective, mosaic. Remember mosaic that we saw with Paulina's example earlier. What else do we have? This is the weights for the loss functions. Label smoothing, if you want to do that. Learning rates, starting and final, momentum, weight decay. Augment is equal to false. Agnostic. So agnostic, non-maximum suppression. Nope. But show is equal to false if you want to show some the plots. So here are the plots. Yep. So these are the arguments for your model. Let's see how much time is left to train it. So it takes, I think, here is like 41 seconds to do one epoch, right? So it's pretty fast. Remember when we spoke about that RNN model and we said that it trains on 48 hours? So this one, it trains in 41 seconds, and then you multiply that by 10. So let's say in 4 minutes. As you can imagine, there's a big difference between 48 hours and 4 minutes, right? And the performances of this YOLO model is, of course, way better than the RCNN model that we spoke about earlier. Here we have some results. This is basically what you're seeing in here, but in a CSV file. Let's check the performances. Well, I don't know these classes, so it's gonna be hard for me to actually interpret if this is a good model or not. But as you can see, it already gives you an idea of what the performances of this model are, at least on the training data set. So while it is training, you can already see what's happening here. Let's let it finish and let's go compare between YOLO V Nano, YOLO V8 Nano, and YOLO V8X. Okay, all good. We are using train 2, not train 1, right? Train 2. Wow. Yes. Okay. 20 seconds left. Here you can check the confusion matrix, the results, some validation batches. And here you can actually validate it fully and get a very detailed validation for it. And then you can just run some inference. And you can deploy whatever model you trained immediately on RoboFlow, but this is not something that I recommend doing. So RoboFlow, we're going to be just using it to train, just to get that first code to actually train the model. And that's it. We're not going to be using it to deploy our models because it's not the best for that. Right? So let's see. Here we go. We got all of our results in here. Let's go train 2 also, and let's see. Confusion matrix seems pretty good, but it is confusing RBC with the background. Let's see the results. Oh, sorry. Okay, so the classification loss function is going down. This one, I think the bounding box loss function and this one for segmentation loss function, they're all going down, which is good. This is the shape that you want to see. But this is for the training. For the validation, it's not really that good. Maybe for the validation, we might require a little bit more training or maybe even more data, right? If possible. The mean average precision score is actually pretty nice. It's not that bad, honestly. And here, the recall, pretty nice. Actually, they're not bad. The metrics are doing pretty well. Let's check train 2 and some. I don't know if this is good or bad, but this looks okay. Here we will do as we said, the actual validation of the model. Let's do it. On the validation data set. And here is where you will be able to just run detect using whatever model was the best, confidence threshold as you wish. And this is the images that you want to run inference on. Okay. Pretty fast. Let's now see how fast it will do the images that we have for validation or testing. Yeah. Oh, wow. Super fast. 0.7 milliseconds to pre-process, 17 milliseconds to run inference, and 3.9 milliseconds to do post-processing, which is non-maximum suppression for you. for an image of this size. This is amazing. So in overall, it's 20 milliseconds. How many milliseconds do we have in a second? I think 60, right?
1000.
Oh, 1,000. Wow, that's a okay. So this is like super fast. This is really good. That's great news then. Yeah, makes sense. So this is it for YOLO V8. As you see, the code actually 0, so it's 0 coding for you. Majority of these models actually work very well, so it's just that they're not maintained very good. But if you want, you could just take a look at one of these models. So Detectron 2, I've already seen it. It's very nice. YOLO V5 is also very nice because it's also in Python. But the other versions of YOLO, since they're not maintained by them, so they will have very bad performances sometimes. You can do some, what is it called, transformers here and experiment with their results, but they are extremely slow compared to what you're seeing right now. And you could do, for example, this YOLO X, YOLO V7, YOLO V3, which is something that I do not recommend using, or any of these different YOLO versions. So use YOLO NAS pretty nice. So now that we have seen how to actually train the model and how fast you can go from actual images, annotate those images, and actually get a working model for those images, let's check how to do it for how to actually understand what mean average precision is. In order to do that, I will just go quickly with a recap for what is precision, what is recall, and then we will speak about what is mean average precision, right? So it's very, very well connected. I'm sure the majority of you already know the concept of accuracy. Accuracy is pretty simple. Let's go down a little bit and we'll see what accuracy is. Accuracy, there it is. So accuracy is a very simple concept. True positives plus true negatives divided by everything. It's very simple to be confused a little bit between the concept, what is true positive, what is false positive, what is true negative, what is false negative. The interpretation for you, just remember that it's two words. The first word means was your prediction correct or not, right? So if you say true, that means your prediction was correct. If it starts with false, that means your prediction was false. The second word refers to what your prediction is. So it does not refer to what the actual image is. It refers to what your prediction is. So if I say true positive, it means I correctly classified it and I classified it as a positive. If I say false positive, which means I made a mistake, it is false. My prediction is false. So I made a false prediction, but my prediction was a positive prediction. So I classified it as a dog, for example, instead of a cat, right? So it's a positive prediction, class number 1 instead of class number 0. So if I say a false positive, can somebody tell me what is the sign, what is the actual sign of that sample? A false positive is a
Negative.
is a negative that is predicted as positive. A false negative is a positive that is predicted as a negative. So just remember these two separations. True means whether your prediction was correct or not. False definitely means your prediction was false. True means your prediction was correct. Positive refers to the class that you predicted, right? So now that you understand this separation, you should not get confused about it, hopefully in the future, because you will be seeing this terminology 100 times. For precision, it's a very simple concept. Precision is equal to true positives, meaning those who are correctly positive, and those who are sharp positive and which were predicted as positive, right? Divided by true positives and false positives, right? So precision simply says how many actually positive classes were predicted positive. So out of those which you predicted as positive, so everything that you said is positive, how many of them is actually positive, right? So if your model just says everything is positive, this is a bad model because it has very low precision, right? It just takes everything as a positive. So this is precision. How many of those you predicted as positive are indeed positive? We go now to recall, and recall kind of is the other way of thinking about it, right? So recall means out of the actually positive samples, so out of the samples which are actually positive, right? Those which are in real life positive, out of those, how many did you manage to predict as positive, right? How many were you able to find as a positive sample? So this is the difference between precision and recall. In our case, we want to combine these two and get a good metric. In usual image classification, you have the common F1 score, which is just the average. Let's see. Oh, they don't speak about it here, but the F1 score, which is simply the harmonic mean between the precision and recall. In object detection, we will be doing something very similar to this, but instead of speaking about what is it called? But instead of speaking about them as, you know, image classification and simple image classification, we will just have to do a small trick to get it to work. So we'll start speaking first about precision recall curves and how can we generate such a curve from the precision and recall values. So very simply, precision recall curve is the different precisions and recalls of that same model when you are changing your threshold, when you are changing your inference or test threshold. So imagine, for example, if I say my threshold by default is 0.5. 0.5 is not the optimal threshold, as we said, for large models, because large models are extremely confident about their predictions. So for a large model, your confidence threshold should be something like 0.75. But since you're using a smaller model, for this one, for example, the nano model, we're going to be using a higher confidence threshold. So let's try the YOLO VX. Not sure if they will run it super fast or not, but let's try it. Let's see. Predict, I think 3 here, right? Okay. So you see the difference. This dog previously was predicted with an accuracy or a threshold of 0.26 or 29, right? For the nano model, but the large model, the extra large model, it predicted it with a confidence threshold of 92. There's no much difference between their actual precisions or their actual results. It's just in the confidence threshold. The other one had a much lower confidence threshold than this one. So let's go back to the other one and see it. Oh, where is it? Prediction 3. Yeah, prediction, yeah, 0. No prediction like this. Yep, let's run. And there you go, you see, 92. And this one did not even predict the backpack. So not that perfect, right? But that's basically the idea behind this metric. So this metric aims at evaluating all types of models. So it doesn't make an assumption on what is the perfect confidence threshold for your specific model. It will use every single confidence threshold from whatever you decide, right? So for example, here, the most common two numbers are from 0.5 up to 0.95 with a 0.05 increases, but it's not really the problem here for us. Let me just confirm it. I think you should have it in the name in here somewhere. Yeah, from 50 all the way to 95. Right, so that's nice. So from 50 all the way to 95 with an increments of 0.05. So as you can imagine, it will go through a lot of confidence thresholds to find that perfect evaluation for your model. And different confidence thresholds would give you different precision recall numbers. What you will do is you will plot these different precision recall numbers along an axis like this, so in the chart, and this will give you a curve like this one. So the area under the curve, this is a common number that you guys probably already heard. So area under the curve, did you study this with Professor Khan? This is a very common metric that is used. So there is area under the curve or there is F1 score. These are different ways to combine precisions and recall in one number to give you some understanding of your model's performances. Did you study area under the curve? Well, it's okay if you did not. It's okay. So even if you didn't, it's really not that big of a deal.
That's
Yeah.
integral, not?
Yeah, it's exactly the integral, but we're using it in this something. It's called area under the curve. It's just another metric similar to, let's say, accuracy or F1 score. It's just another metric for evaluating image classification models. And we will be doing something very similar to it, which is what we call average precision. So average precision is very similar to area under the curve. What you will be doing is the following. You will take a weighted average of precisions based on what? The difference in consecutive recalls. So let's do it. What you will do is, this is the precision. So this number times the difference between this recall and this recall. So it's this multiplied by this. As you can guess, this is already the area of this region. Plus this point multiplied by the difference in consecutive recalls like this, which is the area for this region. So this is what mean precision is, or average precision. And then you'll take this point, multiply it with this difference in consecutive recalls, and you will get this place right here. Same, you will do this, and do this, and do this, and do this. And this will give you the mean precision, or the average precision, sorry, the average precision metric. So average precision is a very simple metric, which is simply the weighted average of the different precisions based on the weights, which are the difference in consecutive recalls. That's all it is. It's a very simple concept to understand. This is average precision, right? So whenever you hear the word average precision, this is also another word for, let's say, area under the curve for classification models. This is something that probably you have seen with Professor Khan, or maybe in some labs or something. And if you did not see it, you will definitely see it in the future courses when you speak more about when you speak more about classification models, or maybe a little bit more in detail about advanced machine learning. You'll definitely speak about this area under the curve metric, which is basically the area under this curve precision recall curve. So this area, the higher it is, the better your model is. So it's an area between 0 and 1, right? So it is between 0 and 1. The higher this area is, that means your model is much better. Your model is correct, and it is very confident about its predictions. It's not just a correct model and gives good results. It's also very confident about its predictions. So it's a perfect model overall for your data set. Now that we have seen how this average precision is good for image classification, we will have to perform one single small step to actually do it for object detection. For object detection, what we do is we do it for intersection over union. With intersection over union, it allows you to convert bounding boxes into true and false values, right? So if we go back here for for accuracy and precision on these things, so what does it take? It takes the following: ground truth positive, predicted positive; ground truth negative, predicted negative; ground truth negative, predicted positive. So it only needs access to these kinds of information. It doesn't understand, or this, right? Or this prediction classification score. It does not understand the concept of a bounding box. So what we will do is we will completely remove this concept of a bounding box simply by applying intersection over union. what we will do is, this is the ground truth. If we see a something that is, or a bounding box that is highly overlapping with the ground truth, we will take that as a positive. If we see a ground truth with zero, predicted bounding boxes around it, that means this is a false negative. This is the way that we calculate false positives and false negatives, right? Or true positives and true negatives. So for example, if I put, this is a prediction bounding box in here. As you can see, there's no ground truth overlapping it. So this is a false. Can somebody tell me false what? So this is a false positive. Now let's imagine that here there is actually a cat. This is the bounding box, the actual bounding box for a cat. This is a cat. And there is no prediction bounding box on top of it. So there's nothing that the model has predicted on top of this cat. So this is a false what? False negative. Thank you. So this is a false negative. If this correctly, this is what is called. This is the real bounding box for a cat. If for some reason I predicted the cat like this, so they have a high overlap, this is a true positive. True negatives, we don't need them because they don't get used in the calculation of what is it called, of precisions and recalls. So if we go down here, for example, where is true negatives? Yeah, this is accuracy. So you see true positive, true positive, false positives. There's no true negatives. And here, if we go to recall, also true positive, false negative, and true positive. So there's no concept of true negative. So because true negatives, we have like hundreds of billions of them. So we're not going to be calculating or evaluating an object detection model for true negatives. True negatives, this is like a given. It must not have like a low true negative. This is impossible to calculate because it will be a very high number and it's extremely useless. But now we have seen how to calculate things like true positives, false positives, and true negatives, right? And false negatives. Now, if I give you this specific example, so this is the actual bounding box, and this is the prediction. Is this a good prediction? Should we calculate this as a true positive? No, this is a bad one, right? This is a bad prediction. So this means that we need a certain threshold for our intersection over union. It doesn't just need to have any overlap with the ground truth to be calculated as a, what is it called? As a as a true positive. It needs to have a high intersection over union to actually be calculated as a true positive. And this is why we will just add a threshold of 0.5 for case coordinates. Two boxes are so close, and as the intersection over union should be around 0.9. It's up to you to decide what your threshold is for calculating the true positives. But that's basically it, right? Plus of the intersection over union, positive if intersection over union is above the threshold, negative if the intersection over union is under the threshold. And this leads us to getting the mean average precision for object detection. So we know average precision for object detection. It's simply average precision, or the average of the precisions using recalls or consecutive recalls as weights for object detection. How do we do that for object detection? As you remember, just intersection over union between ground truth and the predicting boxes. If there is a high overlap, then it's a true positive. There's not, it's a false positive. And then we go down, and what happens is the second M, you see that we have average precision, but we have mean average precision. All that means is we will be doing average precision, but for multiple classes, right? So for example, in our previous case, we had 3 classes. For the COCO data set, there are 80 classes. So what the mean average precision is simply the average of average precisions for each individual class. So this is what mean average precision is and what it means and how it gets calculated. It's a number always between 0 and 1. Of course, 1 being the absolute perfection and 0 being the most absolute trash model possible. If your model has performances or mean average precision above, let's say, 60% or 55 or even 50%, then it is actually a very good model. It depends on how many classes do you have, of course. So if you have like 2 classes or just 1 class and your model is like performing with an average mean average precision score of like 60 or 70%, trust me, this is a perfect model. So unlike, for example, for classification, when your model is like 60% or 50% accurate, then you're like, oh, this is a bad model. In this case, it is actually a very good model if it actually achieves 60% mean average precision score or something similar. So do you have any questions about mean average precision, about YOLO V8, how to train these models, how to evaluate them, RoboFlow, and how to get the data up here, how to annotate the data, and how to export it into different formats? Another quick info. So for Darknet, Darknet YOLO. For Darknet YOLO v4, as you see, the version that is being maintained by RoboFlow is not actually perfect. So preferably you can use this version, which is the original version by this dude. No, not this one, absolutely not that one. It's this one. Yes. So this is the actual implementation of YOLO v4. This version will not have any bugs. This is the perfect version that you should be using. This provides very good performances. It's much faster than the others, mainly because it's written fully in C++. So there's no Python, reducing your speed or performances of your model. And here you can see just different comparisons of different models. Here you see YOLO v7 compared to different types of models. These are, what are they called? These are models that are based on visual transformers. Visual transformers also, these are just big models. This is fast RCNN, remember that one? Here there are the YOLO models, which are all super fast, much faster than the other models in here. And here, this is the actual performance of the model. And as you can see, the best numbers that you could get for a big data set with 80 classes is somewhere around 60%, 50%, even 35, 40% is an actually good model, right? For, of course, lots of classes. So it depends on how many classes do you have. And on this code, you will find implementations for different versions of YOLO. So let's go down here. You'll find YOLO v7s, YOLO v4 with hundreds of different implementations. So all of these different models, though, this is the traditional YOLO v4. This is YOLO v4X with MISH activation function. The MISH activation function, let's take a look at it. MISH versus ReLU. Here we go. This is just the difference. It's a very small difference between actual ReLU and MISH. And there are other activation functions if you see here. So there is Swish also, which is pretty nice. So for the majority of the new object detection models, which are performing very well, it's either with MISH or with Swish, mainly because these activation functions are actual functions that were built by AI. So it's just an experiment where they let AI build its own perfect activation function, and it just keeps on changing the activation function until it found the best activation function. So both MISH and Swish are way better than ReLU or any other activation functions that you know. So you could experiment with them also. So here you got YOLO v4 MISH. Probably you should have YOLO v4 Swish. Here it is also. You got YOLO v4, the small one. There's YOLO v4 Tiny. And there's the YOLO v4 Tiny 3L. So this one performs the classification at 3 layers, meaning, what is it called? Meaning large and medium and small. But YOLO v4 Tiny performs only twice. So if you come here, you will see in the code, there is YOLO 1. So this is for the large ones. And there is another one for the medium ones. So it doesn't do very well for the small objects. So but if you want to maintain using YOLO v4 tiny and, you know, be able to detect small objects, then use YOLO v4 3L, YOLO v4 tiny. Where it is? Yep, YOLO v4 tiny 3L. It does provide very good performances for the smaller objects. Other than that, all of these others, you can just experiment with them. Sadly, they're actually very, very big. So they might take a lot more time to train versus, for example, something like YOLO v4 tiny or YOLO v4 tiny 3L. But even something like the custom YOLO v4, this one, the ordinary YOLO v4, it can be trained on Colab in reasonable time. For example, 1 or 2 hours, you can train it on Colab. And here you will find information about things like batch size, number of learning rates, max batches, which is basically the number of epochs, or sorry, the number of iterations on the data. So for YOLO v4, we're no longer speaking in terms of epochs, we're speaking in terms of iterations, and the iterations is called max batches in here. This is the variable that is called. We have already seen this before, the number of steps, which means the number of steps after which you will be saving the weights of that model. And then let's see non-maximum suppression, non-maximum, yeah, here non-maximum suppression. This is the beta for non-maximum suppression. And of course, the, what is it called? The actual algorithm here, which is greedy non-maximum suppression. The beta, as we said, is the threshold of similarity between the different predictions. And if it exceeds this similarity, we will be removing them and keeping only the one with the highest precision, highest confidence score. Other than that, this is pretty much it. You can get started training this on Colab. Let's try. It's always a pain to actually train a good, what is it called? YOLO v4, because it takes a lot of, how do you say, configuration, but let's see. It should work. Runtime, change runtime type, GPU. Let me just run all. And let's see, run anyways. If it does pass this level of make, we are good. If it passes the make, then we are good. It should take some time. Let's see. I remember last time I worked with it, there was an issue, but it was a very simple bug. For some reason, there was an array that was not being closed. So they they opened an array, but they didn't close it. And just when you close it, it fixes that bug on their code and it works very well. But for some reason, I'm unable to see it here. So probably it's a new bug. Let's see. So far, it seems to be running with just a few warnings, but warnings are expected, so that's nice. So far, it's still compiling. That's good. This is great. It's running. It's compiling. Here it's downloading the weights. And let's see. Still making with just warnings. I think it's succeeding. So I think this version of YOLO v4 is well maintained. As we said, this is the original version of YOLO v4, so that's good. It is something that you could trust. Oh, wow, nice. That's great news. Let's check here. Where is it? It's here, right? So it's still running. It still did not compile, so we can't be happy yet until you find a darknet file in here. That's when you should be happy and you know you passed all the bugs. Yeah, there it is. So we got no bugs. Sorry. So now we have no bugs. This version can be trained easily. Just take your data from RoboFlow. Let me try it again. Export data. YOLO, darknet, show code. Maybe we can actually do it. Done. And let's go down. So it downloaded, it tried, it did some evaluation on basic ones. Now it stops. Now we will need to actually upload our data. Our data should be already uploaded in a good format, so it should not be a problem for us. But let's see. Leave. And let's see. Where is it? Here it is. It's downloading. It should download the data in a very good format. And here we should just give it the location of the data and it should start training. Okay, we need to restart, but it did download everything, so that's okay. Extracted the data to where? Okay, here it is. Now let's try and just run it. Config. Oh yeah. If I'm not mistaken, it's gonna be a lot of work to actually get it done, but let's just do it together just so I can show you how to get it done. Validation data, here it is. Just images, right? There's no config files. Okay, it's okay. So we're gonna have to create 3 files. Maybe we will do this for the next lecture or the next lab. But basically what you will be asked to do is to generate the following kind of data. Here you will see all the information that you need to actually get it done. Data sets here. Yeah. So here you will just need to, not here, train your own model, how to compile, no, how to train our custom data set, yes. So here you will need to create multiple files. First, this is the training file. We already spoke about, we already seen what is inside that file. Here you just remember that you will need to basically change the number of classes. So if we go to the configs, let's see the configs for maybe this. No, this is the weights. These are the weights. Maybe some configs. No configs here. Let's go up. Configs, and let's go for the YOLO v4 tiny because it's the smallest one and it's easiest to actually understand. YOLO v4 tiny. So what you will always remember to change here, number of classes and the number of filters for the first convolutional layer before YOLO layers, right? So here we have the YOLO layer, which is going to perform the actual classification, right? It's going to perform the actual object detection. Here, you will need to tell it how many classes do you have. And here you're going to update the number of filters for this layer based on your number of classes. So remember how much? Let's go back to the lecture just to look at the number. And I'm gonna release you guys in 5 minutes. Let's just go look at that and that's it. It's gonna be a very simple one, right? Canva, let's go. And here we can see that number that we spoke about, the number of filters, which is equal to the number of classes plus 1 plus 4. So number of classes plus 5 times 3. So here we have the formula for us to know what is the number of filters before the classification layer. So you come back here and you must change this number of filters to be 5 plus number of classes, all multiplied by 3. And this is the number of filters for the final convolution or the first convolutional layer before every single YOLO layer. So remember in this YOLO v4 tiny, we said there are 2 YOLO layers. So you must do this twice. But for normal YOLO v4, it will have 3 layers. So if you go here, go all the way down, you're gonna have 3 YOLO layers. As you can see, we have 3 YOLO layers. So you're gonna have to do this task 3 times. And that's it. You can immediately get started training your YOLO v4 models very simply and very easily. So I know that there's been a lot of confusion during this lab. It's a very complicated model. You have lots of different models, YOLO v4, v7, v8. You have different versions, different installations, different libraries. And it's of course not going to be a very simple task. You're not going to be doing a lot of coding, but you will be doing a lot of debugging and a lot of configurations. And I hope that today's lab was at least like a good initialization to how to get you started to all of these concepts. And hopefully during the next lab, I will do this again and give you how to train a good YOLO v4 model, especially since YOLO v4 is actually still one of the best performing models out there. And especially in terms of speed, inference speed, it is still one of the best inference speed models out there. So it's very important for you to learn how to actually get it trained and how to get it used, or how to get started using this model. And of course, the other option would be YOLO v8, which is also very good in terms of performances and in terms of speed. And it's, as we've seen, very easy to use because it's written in Python and it is using very Pythonic, understanding. Do you guys have any questions about today's lab? Oh, good. So next week we will be speaking about segmentation, and we will have a lab about segmentation also. But we will also be speaking. So our task is to train YOLO v4 on your dataset. Absolutely, yes, yes, Paulina, that would be the best thing. But I still did not release the actual homework, so you can get started doing it right away. I will first release the homework on Moodle and allow you guys to submit your assignments. But as you remember, these assignments are not timed, so you can do them anytime. But just remember that it might take you some time to actually take pictures, annotate them, and perform the training for YOLO v4 and YOLO v8. So you should get started as fast as possible, okay? Perfect. So again, I hope this week's lecture was pretty useful, and at least you got to learn a little bit about some good websites and good tips and tricks to actually get started very quickly. And I really am looking forward to knowing about your projects. So do start preparing your projects. Do not forget about those, because next week, not this time, but not the Monday, but the week, the lecture after the Monday, which is just like in a week from now, we will be speaking about your midterm evaluation, or sorry, mid-project evaluation. So just please try to prepare something for that, at least in terms of data sets and initial model training, at least some benchmarks or stuff like that. So very easy, very simple, nothing very big, but you should at least have something ready. As you wish, as you wish. So of course, if you do it for segmentation, it's going to be even better, but if you do it for object detection, it's also pretty good. Any other questions?